Okay, so the next few lessons are going to be a little math intense. The chemistry is a math-based science, so unfortunately you're just going to have to, at some points, deal with numbers and be comfortable with converting them, know how to go in and out of scientific notation, that sort of thing. So there's going to be a lot of examples in this lesson. Take some notes, write some down, especially if there's a particular type or if none of them make sense. Come see me, let's get some help on this. So, first thing I want to cover is what scientists call significant figures. All right, so there's a couple of reasons why we deal with significant figures. Sometimes you're going to do a calculation, you're going to come up with a repeated decimal, like when you do 1/3, you get 3.3333333, or 10 decimals following your answer. There's also, when you're measuring things, you can only measure to a certain amount of precision. All right, if you only have tick marks for every 1/10 of a centimeter, then you can only measure to 1/100th of a centimeter, because you can for sure see the 10th point, and then if it falls somewhere in between, you can approximate that last one. All right, so typically speaking, especially with the tools that we have, 2 to 3 significant figures is the most you can keep when you're doing calculations. So, rules for significant figures, all right, the numbers that matter, that are going to tie into your precision in your calculations and your measurements, are any non-zero, all right, so if it's a non-zero digit, it's considered significant. Zeros that are sandwiched in between non-zeros, all right? And that's because those zeros are necessary to be able to keep that number the same value, all right? So 202, 202 is not the same as 22, right? You need that zero in order to be able to tell it apart from 22, all right? Zeros to the left of the first non-zero are not significant. A lot of times we don't even write these. Like if you're writing 2, you usually just write 2. All right. There's also this is where scientific notation is going to come in. With scientific notation, we can rewrite these numbers without any of those zeros. All right. And then same thing with zeros to the right. All right. So zeros trailing a number typically are not significant. The only time they ever are is if you intentionally put a decimal in there. All right, so if, for example, you write this instead of just 100, that means those zeros are significant. That means you measured it to an accuracy of it being exactly 100. You're not approximating that it's 100, it's exactly 100. All right, same thing here. If with this one, this last zero matters because you intentionally include that after the decimal point, that's communicating that you measured it to 3 decimal places. You have certainty that that's the correct value there. All right, whereas, if you measure something 20,020, that last zero doesn't matter. All right, so there's, honestly, for the most part, it's non-zeros matter. Zeros matter if they're in between non-zeros and if they follow a decimal point. All right? So, do some practice here with your significant figures. I want you to pause the video, see if you can determine how many significant figures are in these numbers. All right? So, non-zeros always count, so these are significant. And zeros in between count because 0.051 is different than 0.0501, all right? But preceding zeros do not matter, all right? So there are 3 significant figures, all right? So next one, all the non-zeros matter. And then all of these zeros fall in between non-zeros, so every single digit in here matters. So there are 7 significant figures. All right? So non-zeros matter. Trailing zeros only matter if there's a decimal, and there's no decimal in this. So there's only 1 significant figure. All right? Non-zeros matter. Trailing zeros, zeros that continue on past the number, only matter if there's a decimal present, which there is in this case. So that means these 2 zeros are significant as well. Okay? So scientific notation helps when you have a lot of non-significant zeros in your numbers. It's a shorthand way of writing out numbers with a lot of trailing zeros or very tiny decimals. All right, so it would take forever to always write out Avogadro's number, which is 6.022 times 10 to the 23rd. All right, that's a lot faster than remembering to actually count all those zeros and make sure you get them right every time. All right, so the rule with significant figures is the exponent, all right, so this number that is written to the top, the superscript number, so these things, sorry, I want my normal pen here, the 23, the 8, all right, that tells you how many times you moved your decimal point. All right, so on, say, Avogadro's number here, our decimal was right there. Then I went and I moved it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 times. Apparently that's not Avogadro's number. So what this should be, 6.022, you're going to keep all of your significant digits. And then, since I had to move the decimal 19 times, it's 6.022 times 10 to the 19th. All right, if I'm moving the decimal to the right, like I did there, or no, sorry, that was to the left, all right, that exponent should be a positive number. If I move the decimal to the right, like with this number over here, I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8 times. It'd be 3.14 times 10 to the -8th. All right? So when you're writing scientific notation, you move the decimal so that you only have one digit in front of the decimal. You maintain any significant figures following the decimal, and then you do times 10 to the exponent that you move the decimal, how many times you move the decimal. All right, so I've got some examples on here. Again, pause the video, try these on your own, see if you can get them right, and then turn the video back on. So again, this is going to be a little bit of a longer lesson. If this totally makes sense, you can always fast forward, but I'd watch a couple of them. All right, so I need to get my decimal here between 5 and 6. So 1, 2, 3, 4, 5. This would be 5.6 times 10. Since I was moving to the right, that's a negative. I moved it 5 times, right? 1, 2, 3, yeah, 5. All right, this giant number, decimal is at the end here. I want to move it here. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8 times. So 4.78 times 10 to the 8th. All right, here I got to go to 7.86. So it's going to be 1, 2, 3, 4, 5, 6, 7. -7 because I'm moving to the right. I'm going to make this 1.673, so it'll be 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. 5.43 times 10 to the -6th. 1, 2, 3, 4, 5. 5.26 times 10 to the 5th. All right, again, if this isn't making sense, talk to me. We'll keep practicing it. So you will run into conversions. All right, these are especially common between English system and metric system. All right, so sometimes you got to think a little bit about these. If you're really, really strong with numbers, you'll probably be able to figure out whether or not you need to multiply or divide. Something I like to do is called dimensional analysis. When we get to Unit 6 and we do stoichiometry, this is going to be a really useful skill set for you to get those sort of problems right. But what you do is I'm converting 200 pounds. So I'm going to take 200 pounds and I'm going to put it outside some parentheses. Inside the parentheses is going to go my conversion factor. All right, and that's this. 1 kilogram equals 2.2 pounds. All right, so when I plug that in, what I want to do is I want to cancel out my pounds and switch my unit to kilogram. All right, so that's where this concept from math class that I'm sure you know, all right, comes in handy. So this 2x times 1 over x in parentheses is the same thing as 2x over x. And I bet you can tell me what happens to those x's. Right? They cancel. Right? So you need the x on the top and the x on the bottom. So if we want to cancel pounds, we need pounds to be on the bottom. All right? And my conversion factor says that it's 2.2 pounds for 1 kilogram. All right? So my pounds cancel. And then math-wise, what I have is 200 times 1 divided by 2.2, which equals 90.9 pounds. All right, other types of conversions you may have involve an equation. All right, so this is often the case with temperature conversions. All right, so here we've got enzymes in the human body work best at 98.6 degrees Fahrenheit. All right, so here's a Fahrenheit temperature that we are given. But the equations we use in chemistry require temperatures to be in Kelvin. Convert this temperature to Kelvin. All right, so these equations, what they have is they have a variable in there for your temperatures. All right, so you would plug Kelvin in for K or Celsius in for F. All right, now these conversion factors are written so that you can solve for one or the other. All right, so if you've got K solo on its own, this is when you solve for Kelvin. All right, you're going to convert to Kelvin. All right, if you've got F written on your own, you're going to convert to Fahrenheit. All right, so based on our question, we have a temperature in Fahrenheit. We want to know what it is in Kelvin. So what type of conversion do we need to do? We need to convert to Kelvin, which means we're going to use this first equation here. All right, so I'm going to take that 98.6, and I just wrote that wrong. 98.6, and I'm going to multiply it by 0.555, and then I'm going to add to 55.37. All right, so 98.6 times 0.555. That is equal to 54.723, and then I'm going to add to 5.37, and that gives me 310.1 Kelvin. All right. So I want you guys to try this one on your own. This really kind of puts everything together. All right. Also ties back into our physical properties. So just in case you don't remember, all right, because this is going to be an equation type conversion sort of thing. Density is equal to mass over volume. All right, that's going to come in handy here. But my suggestion to you, it's easier to deal with the numbers in the calculator if you take this out of scientific notation. Then you're going to plug it in into the equation and solve for the missing variable. So, to do that, 1.173 times 10 to the negative third, that means we moved our decimal 3 spots to the right. So that means to undo it, we need to move it 3 spots to the left. All right, so we're going to take this 1.17 and go 1, 2, 3, and put zeros in there. 0, so it's decimal 0, 0.117. All right, and that is our density. And then what is the correct mass for 250 centimeters cubed? All right, mass is our question mark. We don't know what that is. Centimeters cubed, that's our volume. So let's plug in 0.00117 equals mass divided by 2,500. Now solve for m. All right, so I'm going to multiply both sides by 2,500. Those cancel. 2,500 times 0.00117 is equal to 2.925. So now the question is, which of those answers is right? Because technically these both work. So the question to that, so definitely if you got this one wrong, I'm going to give you the point back on here as long as you gave me one of those two, is this is where your significant figures come in. What's the smallest number of significant figures that we had? All right, so like how many sig figs does this number have and how many does that number have? Got 3 here and 2 there. If you have measurements, the number of sig figs you can have when you're done calculating has to be equal to the smallest number in your measurements. So that makes D the correct answer because that only has 2 sig figs.